Okay, so Glenn, as you know that this is a digital VLSI design. Its code is ECC 503. This is new subject in your fifth semester. And today we will directly start with module number 1. You can see that module number 1. Yes. And this module is basically a review of MOSFET operation and its fabrication. Okay. So do you know MOSFET? Hello.
Yes, sir. Yes, sir.
Can you hear me?
Yes, sir. Hello.
Can you hear me or not?
Yeah, yes.
Okay. Yeah, so MOSFET operation, we will see MOSFET is basically metal oxide semiconductor.
Metal oxide. Yes,
Yeah.
metal oxide.
So let us see what are its functions.
Yes.
Okay, so see what are the objectives of today's lecture. So today's lecture first objective is to introduce VLSI design flow. This exactly will know that what is the VLSI design flow. Then to explain working of MOSFET and various parasitic capacitances associated with it. Okay. Now, after completion of this lecture, what you will know basically, you will know various steps involved in design of VLSI chip. You know the VLSI means very large scale integrated circuit.
Very large
Yeah.
scale integrated circuits.
Yeah. Then you will be able to explain working of MOSFET, and you will see what are the various capacitances associated with MOSFET. These are called as parasitic capacitances. So see, this is overview of VLSI design flow. So basically, if you want to design any integrated circuit, you should know what is to be designed. So you need to treat like a black box. So here I'm pointing out that black box. So any IC is having inputs and any its output. So what you have to do, just you need to imagine that there is a black box. These are the inputs and these are the outputs. Okay. The next page is once you know, define what is input and what is the output. For this specific input, I need this specific output. Then you need to go inside and define its architecture. Architecture means various blocks. For example, you want ALU, arithmetic and logic unit. So in arithmetic and logic unit, there is a logic circuit is there, there is adder circuit is there, there is a control circuit. So you need to define blocks. And afterwards, after defining the blocks, then you need to see that how you can design that adder circuit. You can design that adder circuit with the help of AND gate, NAND gate. Okay. So that is called as functional logic design.
Okay, sir.
And after NAND gate, CC, here it is an AND gate, something like that, AND gate. Okay. And after that, you need to convert each and every NAND gate into transistor level. Yes, transistor level.
Yes.
Because NAND gate is not a device,
No,
but NAND gate is created. But in this
using transistors.
Yeah, in this course, we will only define gates using MOSFETs. Then once that is physical design, then once you do the physical design, then you need to do various types of checks, whether circuit is working properly or not. And if it is working properly, then only you have to go for the fabrication. And once it is fabricated, then you need to test and pack, and finally you will get the chip. Means you have started here with just concept, and after going through all the processes, finally you will get integrated circuit. And this, some of the things you are going to learn in this particular course. Okay.
Okay.
So now all integrated circuits are fabricated with MOSFET. That is metal oxide semiconductor field effect transistor. Its operation is very important. So if you see this MOSFET, this is a three-dimensional view of MOSFET. Can you see here? It is source. Here it is drain. Here
Drain gate. Yeah.
Then whatever you see, this thick oxide. So this is thick oxide, which is also called as field oxide. Field oxide. And here it is called as gate oxide. Okay. This is the gate oxide, small gate
Oh,
oxide.
yes.
This is three-dimensional view, and here you can see here it is two-dimensional view to right-hand side. Can you see this right-hand side? Two-dimensional.
Yes.
Then here it is substrate. Here is also its substrate. Then in substrate there are two regions. Generally, if this is N, there are two types of MOSFET. One is N channel, another is P channel.
P
So,
channel.
in N channel MOSFET, substrate is P type. So this
P type
substrate is P
substrate
type.
N type.
And this is source region, this is drain region. These blue are contacts, this red is gate. This is very thin gate oxide, and where this is thick field oxide. Isolate one transistor from other transistor. So this
Yes.
is the what I say cross two-dimensional view, and this is three-dimensional view. And then this is the physical structure, whatever I have shown. So this is source, which is made up of
Yes.
N plus region. This is drain, which is made of P plus region, sorry, N plus region. And this is the substrate, whatever you see.
P types.
This substrate is of P type.
Mm.
If you
Yes,
want P MOSFET, then substrate
then
is of N type, and this
N
becomes
type and drain is P.
this is oxide, what you see here, and this is gate terminal. So again, this is three-dimensional view of MOSFET. And when it is used in a circuit, so these are the various ways to represent the MOSFET in a circuit. Okay. This is for P channel, N channel MOSFET. In N channel MOSFET, substrate is of P type, and in P channel MOSFET, substrate is of N type. Okay. So this is drain, this is source, this is gate, this is substrate. Similarly, here this arrow indicates N type, and if arrow is placed on source and if it is outside, then it is N channel MOSFET. And sometimes there is no arrow, then it is called as simplified view. This is also N channel MOSFET. Similarly, for P type, substrate, arrow is on the substrate and it is outside, then that is P channel MOSFET. Then here arrow is on source, but it is inside direction. So this is simplified view. And again, if there is no arrow, then at the gate there is a bubble. And if that bubble is there, then that is called as P type MOSFET. Okay, these are the various circuit symbols used in to represent the MOSFET, N channel MOSFET and P channel MOSFET. Now MOSFET operation. MOSFET acts as switch. Switch means to turn on and turn off. Basically, it connects source and drain together. Now MOSFET operation is that when MOSFET get to source voltage, this is gate terminal, this is source terminal, and if this voltage is less than threshold voltage, you might be knowing threshold voltage is basically minimum voltage required to be applied between gate and source to turn on the MOSFET, right? To turn on the MOSFET.
Yes, sir.
If your gate voltage is less than threshold voltage,
MOSFET
MOSFET won't turn on. It will be turned off, right?
Yes.
So therefore, when drain to get to source voltage, as mentioned here, is less than threshold voltage, there is no electron layer, because see, source is N plus, drain is also N plus, but in P-type substrate, so this is P-type substrate, what are holes are there? Okay, this hole, they create here depletion region.
Yeah.
And
Yes.
therefore, when gate to source voltage is less than threshold voltage, MOSFET works in depletion mode. And therefore, since source and drain remains disconnected, depletion means no charge carriers.
Yes.
So therefore, no current will flow through it. Okay. But when we apply gate to source voltage greater than threshold voltage, VTO is threshold voltage. When it is greater than threshold voltage, can you see here inversion layer of electrons just below the oxide?
Yes. Yes.
Can you see my pointer?
That is generated.
So it is mentioned also inversion layer channel.
Inversion layer.
So why this happens basically? Because
Being more than the threshold.
you are applying positive voltage, and there are minority carriers in p-type substrate. Those are electrons, right? And this
Yes,
positive voltage is enough to attract those electrons towards the interface.
Towards it, towards that. Right.
So therefore, inversion of electron is
Towards
created.
oxide.
Just below the oxide. Now n plus drain full of electrons.
One bridge will be formed.
N plus source full of electrons. And thus, when gate voltage is greater than threshold voltage, this inversion layer connects drain and source together, and any small voltage applied between source, drain and source will move these electrons from source to drain, and thus current flows through the MOSFET. And therefore, to turn on the MOSFET, minimum voltage required is threshold voltage or greater than threshold voltage. Now, MOSFET works in three regions. One is cutoff region. Cutoff region means this, whatever I have shown. Here, if gate voltage is less than threshold voltage, no current will flow. And if gate to source voltage is greater than threshold voltage, inversion layer is created as shown here. So that is called a channel. So here also it is mentioned. And when other condition is when drain to source voltage, can you see here? Drain to source voltage. When drain to source voltage is less than gate to source voltage minus VTO, that is threshold voltage, MOSFET works in linear region. So why MOSFET works in linear region? Because if you see here, inversion layer is there at source end. If you, I'm pointing here. At the same time, inversion layer is here at drain end also. Okay.
Yes.
Can you see this? Both the
points? The channel is there, but like linearly increasing.
Yeah, means I'm just pointing out here.
Yes, I know.
Can you see it?
Yeah.
Can you see it?
It's more over here and then less.
Yeah, it's less, but it is there at source end also.
It is connected.
At drain it also it is there, and therefore when this is the condition, okay, then we say that MOSFET works in linear region. Okay. And what is the condition for that? Condition is this one. Drain to source voltage
should be less than ground source.
Yeah. And in that case, current is given by this equation. Can you see here? ID is equal to mu n CO ox by 2 W by L 2 in bracket VGS minus VTO VDS minus VDS square by 2. So where mu n called as this mu n is called as mobility of electrons. CO ox is called as oxide capacitance. Okay. W is called as the MOSFET and L is called as length of the MOSFET. Okay. So in this way, you can find out current flowing in linear region. You have to use, if MOSFET is in linear region, then you have to use this equation. Okay. But suppose if I increase now drain voltage, this drain voltage, let us see what happens. If I increase drain voltage, let us see what happens. Okay. Now you can see here. So when I increase drain to source voltage, so here you can see here, when I increase drain to source voltage, you see here, then what happens? This gate voltage,
Drain incomes less.
yeah, it is not sufficient to
connected.
create inversion of electron
Yeah.
here. Therefore, this point, this depletion region or this pinch off point, it is called as pinch off point, it moves towards source region. Now in saturation region, what happens? In saturation region, there is no channel, entire channel. No channel. Here there is no inversion of electron.
No channel, yeah, not channel connected.
And when this happens when drain to source voltage is greater than gate to source voltage minus threshold voltage. Okay. So when this condition is there, then there is no channel from source to drain. And in this case, what happens? In this case, drain current becomes constant and it is independent of drain to source voltage. And that's why current in saturation region is given by this equation. Half mu N C ox W by L VGS minus VTO whole square. Can you see this equation?
Yes, sir.
See that equation. And in this equation, you can see that there is no drain to source voltage and therefore current remains.
So VTO is?
Huh?
VTO?
VTO is threshold voltage.
Acha.
It is a threshold
Okay,
voltage.
threshold voltage.
Yeah, it is a threshold voltage.
VGS minus threshold, okay.
It's a threshold voltage basically. Okay, now this is characteristics of the MOSFET. So x-axis is gate voltage and y-axis is drain current. And from these characteristics, you will understand that when my input is gate voltage is less than threshold voltage, approximately zero current is there. MOSFET is not on. Okay. And when gate voltage is greater than threshold voltage, current flowing through MOSFET increases as a square law.
Yeah, linearly it increases.
Yeah, it increases as a square law. These are called as input characteristics. Okay. And
yes,
output characteristics are here. Drain voltage on x-axis, drain current on y-axis, right? This is y-axis. When drain voltage is zero, drain current is also zero. When I increase drain voltage, current flowing through drain increases linearly, but up to what point? Up to saturation. Okay, so at this particular voltage, MOSFET enters into saturation. Okay, so at this particular point, this MOSFET enters into saturation. Why it enters into saturation at this point?
That channel is clear, but linear.
Yeah, because here drain voltage is large, na?
Large, yeah, drain voltage is large.
So VDS is greater than
VT.
VGS minus
VT.
VT. Hence, it goes into saturation.
Yes.
While in this portion, VDS is less.
Yeah. Yes.
It is less. So therefore, it is saturation current becomes constant. It is linear, so it increases as a function of VDS. So here also same thing. Here it is saturation, here it is linear. Here it is saturation, is linear. Okay. And in saturation region, current is given by one equation. In linear, current is given by another equation. Okay, you know that.
Yes, yes.
So these are called as output characteristics of the MOSFET. Okay.
MOSFET.
Yeah. Now there is channel length modulation. So what is meant by channel length modulation? Can you see here this one?
Yes, sir.
Yeah, this one.
It's saturation.
Actually, channel is length is defined as this is source channel junction, this is a drain junction, and distance between source and drain is called as length. Okay. But what happens due to as you increase drain to source voltage,
Yeah.
this pinch off point moves towards source.
Towards the source.
Yeah, and therefore length of the MOSFET decreases.
Delta
Okay,
L.
effective length of the tunnel decreases. And since the effective length of the MOSFET decreases, current flowing through MOSFET increases. See here, whatever is shown here,
Okay.
it is increases. Okay, otherwise it would have remained constant. Okay,
Constant.
and because L is in denominator, if it reduces, current will increase. So in order to take that effect into account, this factor is added. Can you see here 1 plus, and where lambda is called as channel length modulation factor. Okay, lambda
Okay.
is called as channel length modulation factor, and this effect is called as channel length modulation. What is meant by channel length modulation? As you increase drain to source voltage, okay, MOSFET enters into saturation region. Once it enters into saturation region, its effective channel length decreases. So this is reducing because pinch off point is moving towards source.
Towards the source.
Because of that, current flowing through MOSFET increases here.
Okay.
Okay, and this increase in current is taken into account by adding one factor, that is 1 plus lambda into VDS, where lambda is called as channel length modulation factor. Okay, and this entire effect is called as channel length modulation. Okay, so if somebody asks you, write down the equation, saturation current equation with channel length modulation, then you need to add that factor. Okay. Without channel length modulation, it is only this much.
Only that. Correct. Okay.
Now these are the various equations here. Can you see here various equations?
So, ID, linear and saturation.
This is NMOS equations. ID is 0. ID is 0 when get to source voltage is less than threshold voltage. Then ID is in linear region when get to source voltage is greater than VT, but VGS is less than VGS minus VT. This is the equation. And saturation current, that is mu n COX by 2 W by L VGS minus VT into 1 plus lambda VDS or VGS
greater than VT.
Yeah. And
VDS greater than
VGS minus VT.
Yes.
Right?
Yeah. Yes, sir.
So you have to remember these equations, right? You have to remember these equations. Similarly, there is a set of equations for PMOS. But since PMOS is in opposite polarity, so therefore all conditions changes. Because P apply negative voltage, right? Threshold voltage of PMOS transistor is also negative. And therefore, if VGS is greater than threshold voltage, okay, then drain current is
0.
Turn on MOSFET, you have to apply VGS greater than VT, but in negative direction. Now, what it means? It means that if VT
got a negative direction.
Negative direction, right? Yeah. So this is linear region. So conditions for linear and saturation are exactly opposite of that of
negative. Yeah.
Okay, so while significance mu p here is this mu p is threshold voltage of MOSFET. Okay, so not threshold, mobility of poles.
No, mobility of the poles.
Again, lambda is channel length modulation of PMOS transistor. This much you have understood? Review of MOSFET operation, everything. So if you want to summarize, you can summarize like this. MOSFET is having 4 terminals: source, drain, gate, and substrate. Okay, there are 2 types of MOSFET. One is N-channel MOSFET, other is P-channel MOSFET. And this is enhancement type of MOSFET. Enhancement. Why it is called as enhancement? Because when we apply gate to source voltage greater than threshold voltage, we are creating channel in the substrate. Okay.
Yes,
And
yes.
that channel connects source and drain together, and therefore any small voltage applied between source and drain will drift all electrons from source to drain, and hence MOSFET turns on.
And so,
Right.
yeah.
MOSFET
Yes,
operation
greater
is
than
divided into three regions. One is cutoff region. When gate to source voltage is less than threshold voltage, no current flows. Okay, because there is no
yeah,
inversion layer.
no, no.
Then,
If I greater than
yeah,
VT and the threshold, then
then
channel will be formed.
yeah, when VGS is greater than VT, inversion layer is formed just below the
Okay.
oxide,
Yes.
which connects source and drain together. When VDS is small, there is channel from
Channel
source to drain.
for social
But
media.
when you increase drain voltage, okay,
Yes.
uh, gate voltage is
Drain,
not sufficient to create the channel at the drain
the drain, so it
drain side.
becomes less from and goes
Yeah,
toward the source.
yes, and
And
because of
then
that,
that lambda is given. Then
because of
this
that,
lambda
MOSFET enters
is
into saturation region.
saturation. Yes. Right. Is
And
that
yeah,
problem?
yeah, and that effect is called as channel length modulation, and because
Channel
of
and
that,
modulation
1 plus lambda VDS is added.
applied. Yes.
Yes.
Yes, sir.
Okay. Now, we will move to MOSFET capacitances. So what is meant by MOSFET capacitance? Okay. So these capacitances are called as parasitic capacitance. And these parasitic capacitances are very important. Parasitic means you cannot see like a lumped capacitor.
Okay.
Lumped means you can touch, you can see. These are
Yes, sir.
different capacitance. If you might be knowing, you have studied
Yeah, yeah.
PN junction diode.
Yeah,
In
yes.
PN junction, there is a capacitor.
Uh,
When diode is forward biased, there is a diffusion capacitance. When diode is reverse biased, there is a transition capacitance. Okay,
yes, sir.
so these are called as parasitics. So if you see, this is MOSFET here. This is cross section of MOSFET. This is top view of MOSFET.
Okay.
Now this is source region. This is drain region. But you can see that some part of source region, drain region, is below this oxide. Can you see this?
Yeah.
So there is an overlap basically. Again, some part of this is entire oxide from here to here. And this is this one. So this is basically practical MOSFET. But if you see ideal MOSFET, I will show you again that ideal MOSFET. See this ideal MOSFET. Okay.
Yes, sir.
So there is no overlap. Yeah, there is, if you see here, there is no overlap of source and drain here. But, and in practically, there is overlap here. Can you see this much is the overlap? Draw it here. So this is the overlap. And this is the overlap. And from the top, you can see this LD distance is overlap. Okay.
Yes, sir.
Because of this overlap, there is a capacitance. And there are two types of capacitances. Now you can see that there are four terminals: drain, gate,
Yes.
substrate, and source. Between each two terminals, for example, gate and drain, there
There
is a
is
capacitance.
capacity.
Between gate and substrate, there is a capacitance. There is a capacitance gate and source.
Source.
There is a capacitance between drain and substrate. Okay. Okay, so
Source
entirely,
and drain.
yeah. So these
Okay.
are called as parasite. Between any pair of the terminal, two terminal, there is a capacitance. If you take gate and substrate, there is a capacitance. Gate and substrate, this capacitance is okay.
Yes, sir.
So these capacitances are divided as oxide capacitance and junction capacitance. Now, oxide capacitances are two types. One is bias dependent and bias independent. Now, if you see here, this is capacitance. When there is a capacitance, this one plate acts as gate acts as one plate, and this N plus region acts as another plate. So there is a overlap capacitance. Okay.
Yeah.
So there is a overlap capacitance, and this is called as gate to source overlap capacitance.
Okay.
And it is given by CO ox is basically oxide capacitance per unit area. If it is multiplied by area, area is W.
Lengthens.
And LD is
Length into width.
overlap area. Width is W width.
W.
Now similarly, gate to drain overlap area. So this is gate to drain
Okay.
overlap area, and this is the
Uh-huh.
capacitance associated. And
Okay.
CO ox is basically EO ox, that is permittivity of oxide divided by oxide thickness.
Thickness. Okay.
Okay. So oxide thickness means this one.
That thick
Yeah.
TOX.
Yeah. Okay, that's the oxide thickness. Now I will show you that what is the W and that I mentioned here. So basically, W is this one, this area. So this here it is mentioned, is which you cannot see in the
That
cross
part,
section.
yeah.
And this is means this much is the area basically. From the top you can see. So this is W and this is LD. So therefore there is a capacitance. So here also it is LD and here it is a W, because this is W and this is LD.
L. Okay. Yes.
Okay. Now, so therefore there are this so therefore this bias overlap capacitances are bias independent capacitances. They are present in all regions, that is MOSFET operation regions, that is saturation, cutoff, as well as linear region. Now there are some capacitances which are bias dependent. Now for example, MOSFET is off. When MOSFET is off means MOSFET is in cutoff region. So which capacitance exists when MOSFET is off? Then gate. So there exists capacitance between only gate and
substrate. Gate and the substrate. Okay.
And that capacitance is given by CO ox is multiplied by W and L, because total entire L will come in picture.
L full thing and this W.
Yeah. But here gate to source. Gate and substrate, no capacitance because no charge comes in this. And gate and source also zero. So this capacitance is zero, gate and this one. Okay.
This is bias dependent.
Yeah. Now when MOSFET is in linear region, so in linear region, you know that there is a channel.
Yeah, that is a channel. Linear.
Now in this case, substrate, there is no substrate will get disconnected from gate. Only there is capacitance between gate and this channel, gate and channel, gate and channel.
Yeah.
So this capacitance is equally divided in two parts. One part is source, okay, and other part is between gate and drain. That is half.
Both half with it, yes.
While gate to substrate capacitance here is zero. Zero. Because no connection of gate with substrate in linear region.
Yes. Okay.
Okay.
Yes.
Then there is a saturation. So in saturation region, you know that there is no channel existing.
Yeah, there is no channel.
Yes, this much part there is no channel existing.
No channel.
Therefore, capacitance will exist between only gate and source.
Gate and source. Yes.
There is no capacitance between gate and drain. And there is no capacitance between gate and substrate.
Yeah, that is also zero. Yes.
And this is approximated 2/3 of total capacitance, because this much capacitance is not coming in picture.
Yes, yes.
So it is taken as 2/3 of the this one. So in this way, this oxide related capacitances will come in picture.
Yes, sir.
Then there is a chart, means what is the total capacitances in linear region. This one, first capacitance is gate to substrate. Here,
Yes.
gate to substrate capacitance.
Yeah, it is actually 0
Yeah,
in
it
linear.
exists only in cutoff region,
It is 1.
but in linear and saturation, its value is 0.
0.
Then gate to drain capacitance. So in cutoff region, there is overlap capacitance,
CFW and
and gate to source, there is overlap capacitance,
yes.
right? In
Yes.
linear region, it is
Yeah,
equally
it is
divided,
half. Yeah.
that there is overlap capacitance,
Yes, yeah.
right? In
That
saturation region, gate to drain capacitance is only overlap capacitance.
0. That
Only
is 0,
overlap.
0.
It is
Yeah,
0, but it is only overlap capacitance is
overlap.
present.
Yes.
And gate to
I have to buy
source,
the
this is 2/3 plus overlap capacitance.
overlap. Okay.
Okay. In this
Yes.
way, these are capacitances. Uh, this part is basically bias independent. Overlap capacitance is bias independent, while rest of
Okay.
the capacitances are bias dependent.
Depend. Okay.
Okay. Now,
Okay.
there are junction capacitances. These are oxide related capacitances, whatever you
Yeah.
have seen. Now, there are oxide capacitances. Okay. Which are oxide capacitances? Now, I will show you here. There are total, how many junctions are there? So this is channel. Channel is of P type.
Yeah.
Okay. And
So
this is
N type,
source
N type,
region. This is source
N
region.
type.
So therefore, there is a junction
E and then N.
channel this side, one.
So
Back side, this is another junction. This is third junction, fourth junction, fifth junction. So there are total 5 junctions associated with drain. There are 5 junctions associated with source. NP, NP, NP. These are the junctions. And in this
yes.
way, all these junctions will, because this is three dimensional.
Yeah. Yes.
So imagine that there is a box, cube. That cube is inserted in
And there is
what
6 also, no? Up also
no,
then.
no, top one will not come in picture, na.
Yeah.
Top there is
So,
oxide. On the top there is
okay,
oxide.
okay, that's full oxide. Okay.
Why rest of the things are covered by P type
There,
substrate.
okay. Yes.
So there these are the things basically. Okay. So these are the MOSFET capacitances. So in this way, today what we have seen MOSFET operation and then MOSFET capacitances. In MOSFET capacitances, there are 2 types of MOSFET capacitances. One is junction related,
Junction
and
and
other oxide related. Oxide related capacitances, there are 2 types. One is bias dependent and other is
bias and
bias independent.
yeah.
In bias independent, there are only overlap capacitances,
Overlap.
and
Yes.
that exist between gate and drain.
Gate and drain.
Okay,
And
that
independent.
capacitance exists in all regions, whether it is
All,
cutoff,
yeah. Yes.
saturation, or
Yes.
linear region.
Linear. Yes.
Linear region. Then in linear region, only to
Independent.
source and gate to drain capacitance exist, and we divide equally
Independent, no?
half. Hmm? That is
Independent.
dependent, bias
Yeah.
dependent. The region
Bias
is
dependent.
bias dependent,
Yeah.
and half.
That linear and this thing.
Yeah, and CGS and CGD are half of total capacitance. In saturation region, only gate to source capacitance exists, and that is
Yes,
2/3 of the total capacitance.
total.
And there are junction capacitances because source region and drain region forms junction with substrate, PN junction with substrate. And there are 5 junctions. One is drain and channel junction.
Yes.
Then bottom side of the drain and substrate. Then front side and substrate, back side and this one, and side one. So total there are 5 junctions, 1, 2, 3, 4, 5, as shown in the figure. Okay.
Yes.
In this way, these capacitances will contribute to CGD, CBG, and CGS. Okay. So
Okay.
these are the things basically today you are supposed to learn.
Yes.
What I will do, I will give you a small numerical. Means, I will just share now whiteboard. Okay, can you see whiteboard?
Yes.
Now suppose this is MOSFET. See, this is MOSFET.
Yes, sir.
Now you have to tell me this is which type of MOSFET. Let me complete. N channel MOSFET or P channel MOSFET?
Sir, N channels.
Okay, if I say this is drain, then this becomes
Source and gate.
this becomes
Gate.
and this becomes
The by
substrate.
Substrate.
Now suppose I connect substrate to ground. I am applying drain 5 volt. Okay. I am applying gate voltage also 5 volt. And I am connecting source to ground. Its threshold voltage is 1 volt. Now tell me, MOSFET operates in which region? First, is this on?
Yeah. No.
On है?
No. Off.
Off है?
Not off.
क्यों off है?
5.
What is
थ्रेशोल्ड के ज़्यादा होने चाहिए.
What is VGS here? How much is
अरे नहीं,
VGS?
थ्रेशोल्ड है. ऑन है.
On है. Okay.
ऑन है.
Then
VGS.
yeah. Second, is it in linear region or saturation region?
Linear.
Linear region. Why? What is the condition for linear region?
That
For linear region, this is the condition.
VDS
Has to be
VDS
less.
is less than equal to VGS minus VT.
हाँ, अभी condition satisfy हो रहा है. VDS कितना है?
Sir, VDS is so 10, 5.
Drain is 5, source is 0, तो 5 volt हो गया ना.
5.
VGS कितना है?
VGS is ये yes 10. Sorry, 5. 5 OS 5 counter. 5 minus 1.
कितना आता है? अभी what is the relation between this? यहाँ कौन सा
4.
relation है अभी? कौन सा side है?
5 is less than 4.
यहाँ पे क्या 5 greater than 4 लिखना पड़ेगा ना ऐसा?
Then
what is the condition? What is the condition?
मतलब VDS is greater than VGS minus VT.
Then MOSFET works in saturation or linear region?
Then saturation.
Saturation. What you said earlier?
It was this. Okay. Linear order.
Okay. Now for P MOSFET, P MOSFET. Now you have to know this. What is this MOSFET? This is P type?
Yes, sir. P type. P type. Yes.
This is source and this is gate. This is substrate.
Gate and substrate.
Let us consider substrate is also connected to source. Source and substrate are connected together. Now consider here this is 5 volt. And gate is connected to 0.
Source is 5 volt.
Yeah, no problem. No.
Okay.
And drain drain is connected to 0.
Okay.
And VT is minus 1 volt. So you have to tell me whether this MOSFET is on or off.
VGS
What is the
minus
condition for the MOSFET to on? For PMOS,
VGS is greater than
VT less than
VT.
VT, PMOS है ये.
Yeah, less than VT. VGS is less than VT. So
कितना है?
VGS
VGS कितना है?
is 5. 5 is less than -1. नहीं,
पहले VGS कैलकुलेट करो और बताओ मुझे. How much is the value of VGS?
5.
आयु कैसा है? गेट कितना है? गेट वोल्टेज कितना है? How you will calculate VGS?
और 0 है ना सर गेट?
हाँ, तो VGS ऐसा
0
कैलकुलेट करते हैं. 0, ये गेट वोल्टेज 0 माइनस
हाँ,
सोर्स वोल्टेज 5.
अरे हाँ
So
माइनस आ रही है.
VGS is -5. and VT is ये -5 ये साइड में
-1.
आया, ये -1.
सर
कौन सा साइन है यहाँ पे?
ये ग्रेटर, ये वही लेस
ऐसा.
देन 5 लेस देन, हाँ माइनस.
हाँ, तो MOSFET इज ऑन है या ऑफ है?
ऑन है सर.
अभी कौन से रीजन में है?
हाँ,
अभी VDS कैलकुलेट करो.
हाँ, अभी VDS लेस देन इक्वल टू VGS माइनस VT.
VDS कितना है अभी, इसका कैलकुलेट करो ना.
हाँ,
-5 होल.
यस हाँ मेरा, हाँ सर -5.
हाँ, VGS तो तुमने कैलकुलेट किया
0 -5
-5.
और ये
हाँ,
-1. VGS माइनस VT.
अभी यहाँ पे VGS, यहाँ पे VT. अभी ये देख लो, ये -5,
-1
ये -5
+1 हो जाएगा.
+1, तो ये क्या आएगा? -4.
-4 हो जाएगा.
हाँ, ये कौन सा है फिर? ये कौन सा साइन देना पड़ेगा मुझे? ये ऐसा देना पड़ेगा या
उल्टा
ये ऐसा?
5 -5. यस.
हाँ, तो ये अगर कंडीशन है, मीन्स ये ऐसा है, तो इफ दिस इज द कंडीशन, देन व्हिच रीजन दिस MOSFET विल वर्क?
तो सर वही अपना लीनियर में.
नहीं ना, ये PMOS है ना. PMOS में उल्टा होता है ना. कंडीशन आर
हाँ, अरे
रिवर्स.
हाँ, कंडीशन भी रिवर्स्ड. अरे हाँ,
हाँ,
सैचुरेशन में.
सैचुरेशन में ना. हाँ, in this way you should be able to know in which region your MOSFET.
P टाइप में वो रिवर्स होएगा तो उसमें.
हाँ, ठीक है.
ठीक है.
Okay, then today we stop here. Okay, okay, I will put the slides on Moodle. Moodle के ऊपर रहेगा.
Okay.
Bye.
Thank you.
Bye.